Creation stories of Pacific Islanders tell us the world was made from a volcano. Other origin myths say the world came from water. But contemporary science tells us that the world evolved from a Big Bang. And the outdated view that this marks an absolute beginning has been used by religious philosophers, most notably William Lane Craig, to revive an old argument for God known as the Kalam cosmological argument. In this film, we'll hear why this argument fails from the very cosmologists quoted by Kalam's supporters. And we'll also hear from leading philosophers of mathematics who will show why the concept of an infinite universe, now being proposed by many physicists, is perfectly coherent. And lastly, we'll see that if the universe did begin, it may not need a cause. The argument is often expressed like this: whatever begins to exist has a cause. The universe began to exist. Therefore, the universe has a cause, and that cause is taken to be God. Let's start at the beginning. Philosophers like Craig have argued that the past must be finite.
If the universe never began to exist, that means that the number of past events in the history of the universe is infinite. But mathematicians recognize that the existence of an actually infinite number of things leads to self-contradictions.
As we shall see, contemporary mathematicians do not think infinity is contradictory, although it's true that philosophers of the past were troubled by it. But even they did not banish the concept. For example, Aristotle distinguished between different types of infinity.
The distinction that he was drawing was between an infinity that's present all at once, all at some particular point in time, which is what he meant by an actual infinity, contrasted with an infinity that is spread out over time, which is what he called a potential infinity. So, for example, if space were infinitely big, that would be an example of an actual infinity because the whole of space is there at any given point in time. On the other hand, if you imagine a clock endlessly ticking, the ticks might go on forever, but if they did, that would be an example of a potential infinity.
But in the 19th century, Georg Cantor revolutionized the mathematics of the infinite.
What Cantor achieved was to treat infinity as a subject of mathematics itself.
It was a whole new branch of mathematics, and it was of breathtaking ingenuity, showed incredible craftsmanship and creativity on Cantor's part.
What Cantor showed was that an infinite set has a strange feature. We might call this the infinite property. That is, it can be put into a one-to-one correspondence with a subset of itself.
We can pair the even numbers up with all the numbers, all the counting numbers all together. So 2 gets matched with 1, 4 gets matched with 2, 6 gets matched with 3, 8 gets matched with 4, etc., etc.
So, for instance, you can show that there are just as many even numbers as there are counting numbers, when intuition should tell you that there have been half as many.
Well, okay, so this just is counterintuitive, and it's counterintuitive because we're used to dealing with finite sets, and what we have to say in the case of finite sets just doesn't carry over to the case of infinite sets. But it doesn't follow that there's anything incoherent about what we say in the infinite case. It just follows that we have to start saying different things in the infinite case.
What you get from most mathematicians, I would say almost all mathematicians, is an uncritical acceptance of infinity in the sense of actual infinity. That's what they need for doing the kind of mathematics that they do.
So one of the first things that mathematicians come to appreciate is that infinite collections do have different properties from finite collections. Things that we absolutely take for granted in the finite case simply don't carry over to the infinite case. And if it's the finite case that is providing us with our basic intuitions, then that means that some of the results about infinite sets are going to be counterintuitive. But that's just what you would expect. Why should the finite and the infinite be the same? As long as we're prepared for these differences again, the very worst that it will be is counterintuitive. It won't be contradictory, it won't be inconsistent.
So one way to bring out the difference between the finite and the infinite is to think about somebody counting. So imagine George is counting to 10 and he's got as far as 5. How many numbers has he got left to count? Well, he's got 5 numbers left to count, 6, 7, 8, 9, 10. But now imagine George is going to count all of the numbers, every single counting number. He's got up as far as 5. How many numbers has he got left to count? He's got infinitely many numbers still left to count. What about when he gets to 10? How many numbers has he got left to count? He's still got infinitely many numbers left to count. So his task isn't going down over time, but when he's counting any finite set, his task is going down over time.
One classic example that Craig has given to show infinity cannot exist is that of Hilbert's Infinite Hotel.
The mathematician David Hilbert illustrates the problem by imagining a hotel with an infinite number of rooms, all of which are occupied. There's not a single vacancy. Every room in the infinite hotel is full. Now suppose a new guest shows up and asks for a room. The manager says, "Sure, no problem." Then moves the guest who was in room number 1 to room number 2, and the guest who was in room number 2 to room number 3, and so on to infinity. As a result of this shuffling, room number 1 becomes vacant, and the new guest happily checks in, even though all the rooms were already full, and nobody has checked out.
It seems Craig is claiming infinity is problematic because the Hilbert Hotel is both full and able to admit new guests. But the problem may simply be the way full is being defined.
If what we mean by full is every room is occupied, then that's true, but it doesn't prohibit us being able to accommodate new guests because we can shuffle them all up, right, in an infinite hotel. If what we mean by full is can't accommodate new guests, then it's just false that it's full.
In Craig's video, a contradiction is supposedly found by considering what happens when the guests leave the infinite hotel.
Suppose all the guests in the odd-numbered rooms check out. In that case, an infinite number of people have left the hotel, and yet there are no fewer people in the hotel. But suppose instead all the guests in rooms numbered 4 and above check out. In that case, only 3 people are left, and yet exactly the same number of people left the hotel this time as when all the odd-numbered guests checked out. Thus we have a contradiction. We subtract identical quantities from identical quantities and get different answers.
The trouble, that video is so below threshold. The complaint in that clip, in particular the one that says that if there are only 3 people left, then there's still the same number of people have checked out as were there originally. That is a feature of infinity that has to be taken on board very importantly, which is that any finite initial segment of an infinite set, if it's linearly ordered, is such that what's left is infinite. So no matter how far you go, in fact, you're still leaving infinitely many elements ahead of you.
There's a formal theory of arithmetic, which is characterized by the Peano axioms. And that's a language where you can express any sentence of arithmetic, like 7 plus 3 equals 10 or something. But when it comes to this Cantorian transfinite arithmetic, there's just no notion of subtraction. It's not well defined to say infinity minus 3. That's not a sentence of either the Peano arithmetic or the Cantorian arithmetic. So while someone might say it informally, there's no formal language where that really makes any sense.
One of the strange things that Cantor showed was there are infinities of different size. The first infinity is known as Aleph naught. The next largest is Aleph 1, and so on.
So there's this infinite number which is called Aleph 7, and there's also an infinite number which is called Aleph 5, and we can add those. And if we add Aleph 7 to Aleph 5, you might think that what we're going to get is Aleph 12. But it doesn't work like that. The infinite case is different from the finite case. In fact, what happens if you add 2 infinite numbers together is that the bigger one swallows up the littler one. The smaller one is insignificant compared with the bigger one. And Aleph 7 plus Aleph 5 is just Aleph 7. Aleph 7 just takes over, and it's as if the Aleph 5 wasn't even there. So Aleph 7 plus Aleph 5 is Aleph 7. And similarly, Aleph 7 plus Aleph 3 is Aleph 7. If you add these smaller infinite numbers to Aleph 7, you just get Aleph 7. Now, suppose we tried to perform a subtraction. Suppose we start with Aleph 7 and ask, what is it that you need to add to Aleph 7 to get Aleph 7? Now, unfortunately, there's no clear answer to this, because we saw that if we added Aleph 3, that would just give us Aleph 7. If we added Aleph 5, that would give us Aleph 7. There's no longer any such thing as the number that we need to add to Aleph 7 to get Aleph 7. And this is an example of how subtraction just isn't well defined in the infinite case.
You could say the same about 0, that 0 divided by 0 isn't defined. In fact, anything divided by 0 isn't defined in normal arithmetic. But that doesn't mean division is meaningless or that 0 is contradictory.
As we saw earlier, when presenting to a lay audience, Craig has claimed that the infinite is contradictory.
But mathematicians recognize that the existence of an actually infinite number of things leads to self-contradictions.
But when talking to philosophers, a different claim is made.
Now, Alex is certainly right that when we appeal to these absurdities, we are not talking about logical contradictions or incoherences. Jose Bernardet, in his book on infinity, says that there's no logical contradiction involved in these monstrosities, but you have only to look at them in their concrete reality to see that this is metaphysically impossible.
In contrast to other notions of possibility, metaphysical possibility is far less clear what the definition of that is supposed to be. And many of us are dubious that just simply pointing that something seems absurd is enough to forbid it from existing. In reality, philosophers have to be a lot bolder than that. A lot more open-minded.
Hotel case is so basic that that's no place for anybody to dig in their heels against infinity. Even if you only accept potential infinity, the Hilbert Hotel and those results about it are completely incontrovertible.
The examples that are supposed to be problematic always involve admitting new guests, shuffling guests from one room to the other. And if we imagine a hotel where the doors were sealed and nobody could move from one room to the other, it's hard to think of a similar example that could bring out anything that looked absurd about it. It would just be a hotel with infinitely many rooms in. And if that's right, it does lead you to wonder whether the problem is the infinity involved or whether it's the manipulation of those infinite elements that's the problem. And that's helpful because, it's plausible to suppose that what's done is done and you can't change that. The past is fixed and unchangeable. So that if the past is supposed to be like an infinite hotel, then it's more like one where the guests can't shuffle around than one where they're free to move to different rooms. It's just impossible that yesterday didn't happen, given that it has happened.
Another example given to try and refute infinity are the orbits of Jupiter and Saturn.
Suppose that for every one orbit Saturn completes around the Sun, Jupiter completes 2. The longer they orbit, the further Saturn falls behind. Now, what if these two planets have always been orbiting the Sun from eternity past? Which has completed the most orbits? Strangely enough, the number of their orbits is exactly the same, infinity. But that seems absurd, for the longer they orbit, the greater the difference becomes.
If they were always orbiting, then there is no notion of one being at any given point having gone twice as many times as the other. That just doesn't make sense.
The hypothesis is not that they start orbiting at some point in time and they've done 0 orbits at that point. But if the hypothesis is that they'd always been orbiting, then it's just the case that they've both always done infinitely many orbits. There's no sense in which you could draw a graph that they start at 0 and then diverge away from each other and then one of them catches up or something. They're just both always having done infinitely many.
Infinity is accepted by mathematicians. So what about physicists?
So in regards to infinities in physics, the only obstruction that we have is an observer cannot measure an infinite number because infinity is not a number. Things that are observable cannot be infinite, but things like the entire volume of a space or the entire duration of time can be infinite as long as an observer cannot measure them.
Roger, why don't you start with the absurdity of a Hilbert hotel, that you can't...
It's not an absurdity, it's just what happens if you have infinity. I mean, that was the major thing that Cantor had showed you can talk about infinity in a serious way. And you deduce very powerful results from talking about infinity in the right way. You have to be careful when you talk about infinity, but yes, if you're careful, talking about infinity is perfectly reasonable. So I can't see a general statement about infinity is not physics.
I think what Roger's probably thinking is what I would think is that there's certainly a well-defined mathematical description that one can imagine where there's some function that's defined for all time that describes what's happening at all time, maybe a wave function that evolves with time and is defined for all time. How did we get to now question really just doesn't arise. At the time T0 that we call now, the wave function says that certain things are happening. And if that's an accurate description, that's what's happening. One doesn't have to start at the beginning at minus infinity and go through all the times to get to now. One is just here, now.
Craig claims that the infinite past is impossible because one can't reach infinity by successive addition, which is true if you only have a finite amount of time. But what if you have an infinite amount of time? Could you count all the numbers then?
Yes, if you're counting forever, if you're never finishing, there is a sense in which you can count them all. And it's the following sense. Given any individual counting number, however big, 1 million, 1 billion, 1 trillion, you'll eventually get there. It doesn't mean that you ever will reach the point that you can stop and say, done it, I've now finished, I've counted all the infinite numbers. That never happens. However far into the future you go, you've still got infinitely many numbers still to count. So no, this isn't a task that ever terminates, but we didn't claim that it did. The claim was only that you can count infinitely many numbers in an infinite amount of time.
Okay, so sometimes the problem is supposed to be that we can't transition from the finite to the infinite. After all, if we've got something finite and we add a finite amount to it, then the result's going to be finite. So no matter how many times we do that, we're never going to break out from the finite to the infinite. The problem is not so much that that's false, and it seems to me that that's true. It's just that the hypothesis of the past having no beginning is such that it's always been infinite. There's never been any point in the past where there'd only ever been finitely many. So there's no need for a transition.
So you never get to the end of this process. You never get to the last biggest counting number. This is a sequence. The sequence of counting numbers is a sequence without an end. But that's perfectly acceptable. That makes perfectly good sense. The fact that you can't get to the end is indicative of the fact that there is no end.
Suppose we agree the infinite is impossible. What does that mean for the infinite future? Supporters of the Kalam are generally committed to this idea, not just because religious texts seem to promise it, but also because some allege that our lives have no meaning without it.
That on a naturalistic worldview, everything is ultimately destined to destruction in the heat death of the universe. Our moral lives become vacuous because they don't have that kind of cosmic significance.
I still need to have you explain that for me better, because again, it seems to me it's one thing to say it lacks eternal, cosmic, everlasting significance. Mm-hmm. It's another thing to say it lacks significance. In fact, to give one of your examples, you talked about, again, I don't remember the source of this quote, but the torturers, was it Nazi torturers?
Right, yeah.
And you say, if theism isn't true, then it doesn't really matter. This strikes me as I'm sorry, I'm sure it's going to sound rude, but it strikes me as an outrageous thing to suggest it doesn't really matter. Surely it matters to the torture victims whether they're being tortured. It doesn't require that this makes some cosmic difference to the eternal significance of the universe for it to matter whether a human being is tortured. It matters to them, it matters to their family, it matters to us. So again, how do you move from the lack of eternal significance to the thought that if it doesn't have eternal significance, it can't have any significance?
Because the victim, it obviously matters to him in the sense that he's in pain and agony. But ultimately, it doesn't matter that he was ever in pain and in agony. The whole thing just degenerates into utter meaninglessness and insignificance.
It's hard to see how someone can claim that infinity is incoherent and then state that our lives are meaningless unless they are eternal. After all, the infinite future seems to have remarkably similar properties to an infinite hotel.
If you think about the number of events in the future as like equivalent to the number of guests in the hotel, and then as time passes, we're removing an event from the future and putting it in the present. And we can ask how many events are there left in the future. It's the same number of events in the future as there were before that event entered the present. So even though we've taken one away, we've got the same number left. And that's exactly the same property. It's adding one guest and having the same number of guests after adding it in. So if one of them's problematic, so is the other.
If the idea of infinity is putting pressure on the idea of an infinite past, then it's going to put equal pressure on the idea of an infinite future. There's no clear asymmetry there that means that one of those is problematical in a way in which the other isn't.
Craig's response to this problem is to suggest that an infinite past would be actual, but the infinite future would only be potential.
And it seems to me that this rests on a mistake, because Craig, instead of focusing on the question, how many future events will there be if the future is endless, to which the answer is infinitely many, Craig instead switches to how many future events will have been. And that, it's true, is always finite and increasing over time and approaching infinity but never getting there. But its problem is that those two things are compatible with each other. And for one thing, it's changing the subject. If you say how many events will there be, and to answer in terms of how many events there will have been, it's changing the subject. But also, they're both true. I mean, even though there will have been finitely many events, it's also true that there will be infinitely many events. I mean, in the infinite future, those two are not incompatible with each other.
The infinite future is not the only infinity supporters of the Kalam tend to embrace. They've also claimed that the Big Bang singularity proves a beginning of time.
Arrives at a state of infinite density at some point in the finite past. This state represents a singularity at which space-time curvature, along with temperature, pressure, and density, becomes infinite. It therefore constitutes an edge or boundary to space-time itself.
The argument by Lane Craig that the fact that there's that the infinite past is impossible, and therefore that conception of the universe is untenable, is incompatible with their claim that there is a singular point at which the universe originates, because the properties of that singularity are entirely infinite.
Precisely what a singularity is, as John Barrow has forcefully emphasized, is something that involves a kind of actual infinity. For physical reasons, involves a kind of actual infinity. And this is precisely what these very same thinkers said that they were suspicious of. So to put it very bluntly and very crudely, are they trying to have their cake and eat it, accepting an actual infinity in one context while trying to dismiss it and being suspicious of it in another context?
Mathematicians do not think infinity is contradictory. What may be contradictory is claiming that infinity is both a contradiction and not a contradiction. claiming that the infinite past is incoherent when the infinite future is embraced, and claiming that the beginning of time is confirmed by the Big Bang singularity, which itself involves infinities. A further problem for the Kalam argument is that it assumes an eternal universe would have had to traverse infinite time in order to get to a unique now. But in relativity, there is no such notion. Time is relative. In order to tackle this, Craig appeals to what is known as the Neo-Lorentzian interpretation of relativity, which does restore a unique sense of now.
Discovery with Copernicus is that the Earth is not the center of the universe. Well, but you can always rethink the Earth you can imagine that you can add a center. Nobody prevents you from doing that. You just complicate life for yourself. And it's the same for special relativity. You can add a preferred reference frame. It's not visible, it's not detectable, but you think it's there. That's the Lorentzian, the Neo-Lorentzian interpretation of special relativity. What do we gain? The only thing we gain is that we can do the new physics with the old mindset. But I think we should adapt our intuition to the new physics, not adapt new physics to our intuition. Right? When we discover that the Earth is round, that's up, that's down, but if you're in Sydney, it's the other way around. Well, you can think, yeah, but in reality there's a true up and a true down. You can, but what do you gain? I mean, you have to adapt your intuition about up, down to the discovery, not the other way around. Physicists are not particularly keen about Neo-Lorentzian interpretation of special relativity. Having said that when you go to general relativity, have a Neo-Lorentzian interpretation is much harder, because in special relativity you just pick a frame and you. In general relativity there is no global frame to. I think everything in physics, modern physics, is telling us that there is no preferred frame, there is no preferred time slice, there's no preferred time.
Craig has suggested there is a universal clock that gives us a unique now. That is cosmological time, the time since the Big Bang.
Cosmic time is the same for every hypothetical observer in the universe, regardless of his state of motion. In other words, cosmic time is a kind of reinstatement of Newton's absolute time.
Well, cosmological time is a fake. Why? Because matter, gravity slows time. So inside the galaxy, clocks go slower than outside. Point is that there are many different clocks in the universe, which they don't agree with one another, and there are many times in the universe which don't agree with one another. The idea of the cosmological time is just one arbitrary definition of an average, but I can give a different definition of an average.
What about cosmology? Doesn't the Big Bang imply the universe had a beginning? The Penrose-Hawking singularity theorems that supposedly proved this have assumptions that almost nobody in cosmology takes seriously anymore. In particular, most physicists think Einstein's theory of gravity will need to be modified to take into account quantum or other effects that arise in the extreme conditions of the Big Bang. This isn't just the consensus of cosmologists, but the views of the very authors of the singularity theorems, Roger Penrose and Stephen Hawking.
The real lesson of the singularity theorems is therefore that we need to combine the general theory of relativity with quantum theory in order to understand the origin of the universe.
It is certainly a view quite commonly expressed now that we shouldn't simply give up that the Big Bang is a singularity, that we need a theory which describes that. Most people would say it's a form of quantum gravity. I have a view which is different from that, but nevertheless, I have in common with that we need a new theory.
I don't think anybody believes that the universe started off with the singularity. That just tells us that Einstein's classical theory of general relativity breaks down. So that classical theory of gravity doesn't apply when you get to very high energies. So it's replaced by some quantum theory, consistent quantum theory of gravity. String theory is a candidate.
Standard Big Bang cosmology, which was a hot Big Bang, right? You start with a very hot, dense universe, and which begins at singularity. So that picture I don't think anybody believes.
Many scientists have taken our best candidates for a quantum theory of gravity and analyzed the Big Bang. Models inspired from string theory often show that the Big Bang was not the beginning, and a frequent result is that there was a contracting era that preceded our expanding universe.
There had been an evolution of the universe which was some kind of mirror image of what happened afterwards. So in the same way as the post-Big Bang era where we live, in our model will last forever, and I think it also lasts forever in ordinary inflation, okay? For us, because of this symmetry, this duality, also the past is infinite, okay? The future and the past are both infinitely long.
String theory's main rival, loop quantum gravity, seems to show the same thing.
If you reverse the film, so to say, of the evolution of the universe and went back in time, the universe was contracting, and then instead of reaching a zero volume, in fact, when it reached the curvature became Planckian, then new quantum effects come into the picture, and they cause the universe to bounce.
Any theory that has some kind of discrete space, then by definition there you don't hit the singularity. That could be an explanation of why all these models they somehow go to this bouncing solution when we arrive at a very small scale.
With the physics community abandoning its belief in the applicability of the Penrose-Hawking theorem, Coulomb advocates switched to a newer theorem, known as the Borda-Guth and Vilenkin theorem, or BGV. This theorem was developed because the period of rapid expansion, known as inflation, that's believed to have taken place in the early universe, violates one of the assumptions of the Penrose-Hawking theorem, that gravity is always attractive. Inflation is also thought to be eternal into the future, creating an infinite multiverse.
In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin were able to prove that any universe, which is on average in a state of cosmic expansion throughout its history, cannot be infinite in the past, but must have a past space-time boundary. What makes their proof so powerful is that it holds regardless of the physical description of the very early universe. So in fact, the Borde-Guth-Vilenkin theorem does imply an absolute beginning of the universe.
I was working with Arvind Borde and Alex Vilenkin to understand what we can learn about how inflation might have started and how far back it could have gone. And in particular, once we realized that inflation could be eternal into the future, it seemed like a very natural question to ask, could inflation have also been eternal into the past? And what we found was that inflation could not be eternal into the past. What we basically managed to achieve was proving a theorem which says that any expanding region of space-time that has some minimum expansion rate can only go back so far, and not infinitely far. So that means that inflation must have had a beginning. It doesn't really say that the universe must have had a beginning, but it says that the universe could not have been expanding forever up until the present time.
So we interviewed by Ashtekar, and in their model they have a bouncing universe, and they said, well, that means the universe could be eternal in the past, and that theorem doesn't prevent that. Is that right?
Yeah, that is right.
The theorem proves that inflation must have a beginning, right? The universe as a whole, the theorem doesn't say that. It says that the expansion of the universe must have a beginning, right? So, but it opens the door somewhat for alternatives.
As we've seen, one way to avoid the BGV is to have a past contracting universe, which is also a common prediction in multiple approaches to quantum gravity. But some suggest that this collapsing phase will be messy and unstable, and therefore not be able to transition to our smooth, homogeneous universe.
We have absolutely no idea of what exists in the universe before the bounce. So it's very speculative and very difficult to decide whether the situation is stable or not. And even in the case where the situation is unstable, usually what it means is that the simplifications we use in standard cosmology cannot be used anymore. But you know, nature doesn't care about the fact that it is hard to calculate. So when we say that something doesn't work, most of the time it means that the model we use to describe these things doesn't work anymore. For example, you cannot use the Friedman equation because the universe is so inhomogeneous that the Friedman equation is not usable anymore. So what? The universe doesn't care that we have to invent another equation. I think the correct way to think is not to go from the past to the future, is to start from what we know. What we know is what we see around us today. The universe is expanding. We have stars, we have galaxies, we have gravity. We have a theory. And then we go backward in time and we see what happened. And in our theory, when we go backward in time, we do not end up with a singularity. We end up with a bounce.
The BGV theorem relies on principles of relativity. For example, signals cannot travel faster than light. But this is problematic for Craig's Lorentzian relativity, which allows for faster than light travel. And with the authors of the BGV explicitly stating it does not prove the universe had a beginning, the Kalam advocates have begun using yet another theorem developed by Aaron Wall.
Wall is assuming that some version of second law of thermodynamics is really fundamental and should be a fundamental ingredient in this series which determine whether there will be singularity or not. And I agree with that. I think that it really is something that would emerge in approximate sense in a semi-classical regime.
Generalized second law that was proven by Aaron Wall for quantum singularity, it assumes an infinite space. And if you don't allow for infinities in your theory, then you cannot take that theorem seriously either.
Craig also quotes a paper by Anthony Aguirre and John Cahias that he claims closes the door to a past eternal quantum gravity era. But in most models, the quantum gravity era is brief anyway. And the paper only referred to a particular model known as the emergent universe.
But there are other possibilities too, as to how the universe could be in accord with the Bordet-Guth-Vilenkin theorem, but could, I think, really be past eternal. If you define a past eternal model, you can. It self-consistently works, but you do have an edge to it. If you can ask what's beyond that edge, and it's another copy of the same universe. So I think where the debate lies, past eternal models exist. I think some of them are flawed, like the emergent model. I think you can't really make a self-consistent model that stands up. Past eternal inflation or the steady state model, I think you can. But you have to do it carefully, and there's an interesting then answer to what is this Bordet-Guth-Vilenkin theorem pointing to? It's pointing to something very interesting. It's just not in initial time.
Just as there are theorems that prove the universe had a beginning, there are also theorems that imply the opposite.
I think you can prove anything. Theorems are very strange things, because you can have a theorem to prove anything as long as you assume the right things. In a way, that's a problem. And you know, you can violate any theorem as long as you violate the assumptions.
Of course, there are the singularity theorems, but you can always interpret them as telling you that a quantum theory of gravity should not have one of the hypotheses that you are using to formulate this theorem.
The Big Bang doesn't prove the universe had a beginning, only that it evolved from a very hot, dense state. But when it comes to physics, the Kalam advocate has another card to play: the second law of thermodynamics. The second law states that entropy, which is roughly a measure of disorder, increases with time. And so the argument goes, if the universe were eternal into the past, we would already be in a maximal entropy state. Since we aren't, the universe can't be past eternal. This also related to the mystery of why the Big Bang was in a surprisingly low entropy state. But what if the universe were infinite?
Perhaps we're living in a physical system where there's no maximum possible entropy. Suppose the entropy can just grow forever. And an eternally inflating universe looks like such a system, although nobody really knows for sure how to define the entropy of an eternally inflating universe. But if it's the case that entropy can grow forever, then any state is a state of low entropy because it's low compared to the maximum, which is infinite.
What we need to consider is not just the entropy of matter, but also entropy associated with horizons, so to say the gravitational entropy. In the contracting branch, because the dynamics is different from Einstein's theory, a horizon develops, but it grows extremely rapidly. This entropy dominates completely the entropy of matter. Therefore, the entropy is really growing very rapidly, but then at the bounds, the geometry is such, which is non-trivial statement, is such that in fact the area of this horizon becomes infinite. And then after that, the horizon simply disappears. So if you like, what one has to do is to reset the entropy clock in a certain sense at the bounds.
These are just two of many potential solutions to this entropy problem, which are explained in our film series Before the Big Bang. The fact that there are several options tells us entropy does not prove a beginning. What if the universe did have a beginning? In the 1970s, Edward Tryon claimed the universe might arise as a quantum fluctuation of the vacuum. But this still raises the question, where did the vacuum come from? In 1982, Alex Vilenkin suggested that if space itself was treated quantum mechanically, it could quantum tunnel into existence. He titled his proposal, Creation of Universes from Nothing.
Now, sometimes skeptics will respond to this point by saying that in physics, subatomic particles, so-called virtual particles, come into being from nothing. This skeptical response represents, I believe, a deliberate abuse of science. The theories in question have to do with particles or the universes originating as a fluctuation of the energy contained in the vacuum. The vacuum in modern physics is not what laymen understand by vacuum, namely nothing. Rather, in physics, the vacuum is a sea of fluctuating energy governed by physical laws and having a physical structure. To tell laymen that on such theories something comes from nothing is a distortion of those theories. Properly understood, nothing does not mean just empty space. Nothing is the absence of anything whatsoever, even space itself. How silly then when popularizers say things like nothingness is unstable to quantum fluctuations, or the universe tunneled into being out of nothing.
When we say nothing in this context, tunneling from nothing, we don't mean quantum vacuum. It's actually what Ed Tryon meant. Here we have a state without space completely. So there is no vacuum.
But if the universe did quantum tunnel into existence, what caused it?
Many quantum mechanical processes do not require a cause. So for example, if you have a radioactive atom, you know that it will decay, but you cannot tell when. There is a half-life time. For example, you can tell that in a year, the probability for this atom to decay is 50%. Then the year has passed, it didn't decay. The probability for it to decay the next year is still 50%. Eventually, it will decay. But if you ask why did it decay at that particular moment, there is no reason. There is no cause. So quantum mechanical processes like this are uncaused. The spontaneous creation of the universe is of the same nature.
The notions of quantum mechanics place severe pressure on our everyday ideas of causality. You might say, well, there are some interpretations of quantum mechanics that allow for causality and determinism, and it's true there are, but then there are other interpretations that don't.
Since the Kalam asserts that everything that begins to exist has a cause, its defenders carry the burden of proof to show causality is maintained in quantum mechanics.
So the different interpretations of quantum mechanics do differ a lot in terms of the role of causality. Start with the Bohm interpretation, or Bohmian mechanics, or the pilot wave theory. That is the most like classical mechanics when it comes to causality. Causality is deterministic, and cause necessarily follows effect according to the law. A bit of a more of a deviation from the classical approach to causality comes in collapse theories, dynamical collapse theories, or the GRW approach. And these theories have irreducible randomness in the way the world turns out. So, an effect need not necessarily follow a cause. A given cause could lead to many effects with different probabilities of each one. And there would be nothing in the world that explains why one effect happens rather than another. Any of them could have done. It was just random. And so that weakens the link between cause and effect. Instead of being ironclad necessity, it's probability. The cause makes the effect more probable. And I think that's a big change to the role of causality. But there's a bigger change still, potentially, to the role of causality in the many worlds interpretation, or the Everett interpretation. People often call that a deterministic interpretation, in that they say we have the quantum state of the universe, and deterministically there evolves a multiverse, a system of many parallel worlds. But there's an open question as to whether we should call that process causation, and we should call that causality. My own preferred approach to understanding many worlds has it that causality is a process that goes on within each individual world, but not outside or between them. So causation is an emergent process that emerges along with the individual worlds, but is entirely contained within them. And that is perhaps an even bigger change to the concept of causation, because it means it's non-fundamental. It's not part of kind of the deep structure of reality. It's not a concept that's even really properly applicable at the level of the whole universe.
In the Copenhagen interpretation, things are acausal simply because it's kind of built in the nature of interpretation. You have a wave function describing your atom, and then the wave function collapses in the course of measurement, resulting in some of the outcome probabilistically. And there is no cause how you choose these things. In the case of many worlds, this wave function describes an ensemble of universes. And in different members of the ensemble in different universes, you get all possible outcomes of your measurement. Simply, you don't know which universe you are in. And which universe you end up in is also an acausal kind of process.
In defense of the argument's first premise, Craig makes use of de Broglie theory, also known as pilot wave theory. And in defense of the argument's second premise, Craig makes use of Neo-Lorentzianism. Now, at least amongst physicists, both de Broglie theory and Neo-Lorentzianism are considered to be fringe and disreputable. Therefore, although Craig might seem to be simply appealing to common sense or to mainstream science, Craig is actually appealing to theories that do not enjoy wide philosophical or scientific support.
I think one of the basic lessons you can learn from an advanced science of any sort is that common sense and intuition only takes you so far, and beyond a certain point, you really can't trust it. Russell once made the argument that since physics is really a systematization of our common sense approach to the world, his argument was, well, if common sense is true, then physics is true. And if physics is true, then common sense is false. Therefore, common sense is false.
If something could come from nothing, then why doesn't this happen all the time? Why don't tigers just appear in our living room?
In quantum mechanics, many things are possible that are not possible in classical physics. And indeed, you can have, in principle, you can have very strange things happening, like objects coming out of thin air. A lump of matter, in principle, it can turn into a tiger. And quantum mechanics will not tell you that this is absolutely impossible, but if you try to calculate the probability of this happening, it will be pretty low. If you think of the quantum creation of the universe, it is a tiny microscopic universe, right, that has to pop out of nothing. If you calculate the probability of this happening, I should say that conceptually this probability, interpreting this probability is a little difficult, but still, if you do the calculation, you find that it is far more probable than having a tiger materialize in front of you.
The argument that something can't come from nothing, or perhaps it'd be better to say something won't ever come into existence following nothing, isn't really confirmed by our everyday experience, because in our everyday experience we don't ever experience a nothing and check it to see whether something can or can't come from it. So there's no argument at all, I think, on the basis of what we've observed in everyday life at all, to think that something can't come from nothing.
It isn't just quantum mechanics that divides thinkers about the nature of causality. Philosophers are equally unsure of its merits.
So causation is a classic philosophical topic in the sense that there's no agreement about it at all, and there hasn't been ever.
There's lots of schools of thought about what causality is. At the one extreme, we've got a view like that of Russell, which you might call the eliminativist theory of causation, according to which really there isn't any such thing as causality. Russell said if you look at the physics, certainly the physics of his day, and I think it's plausible to say about physics today as well, you know, it consists of equations, for instance, differential equations, and these relate states of a system at various times or at the same time, but they don't mention causal relations at all. And Russell's view was that the more developed a science is, the less appeal there is to causality in it. At the other extreme, or at least some way towards the other extreme, you've got views like the counterfactual theory, which says that A causes B means that if A hadn't happened, then B wouldn't have happened. But there are complications with trying to work out what exactly that, what's called the counterfactual, is supposed to mean, and that might in turn appeal to causality. So it may not even be a full account of causality at all. Or even further along the line, you might have a full-blown sufficiency account of causation, according to which A causes B means that A somehow makes or forces B to happen. And in between these extremes, there are all kinds of different theories. So it's a bit implausible if you assume, as the Kalam argument does, that whatever begins to exist must have a cause on the basis of our intuitive conception of what causality is. The intuitive conception of causality is vague and it covers a whole range of different things, and you really have to be clear about which one you mean more precisely before that argument can be given any force.
If the universe had a beginning, it's hard to see how it could have a cause. After all, we tend to think of causes happening before their effects. But if time began with the universe, then there was no before. So how could God have caused it?
And I frankly just don't understand why people think that causality is a temporal relationship. For example, philosophers talk all the time about cases of simultaneous causation, where the cause and effect occur at the same moment of time. Immanuel Kant gave the example of a heavy ball resting on a pillow, causing a depression in the pillow. Now, the ball and the pillow could have existed from eternity past.
This seems like the admission of something that's existed for a past eternity. So it may be that Craig, by using this example, is allowing, and he may not consistently be able to allow, that something's existed for a past eternity.
In physics literature, there is no such thing as simultaneous causation. So the notion of causality in physics always has a chronological nature, that basically the cause should precede the effect. And in this particular example of the ball and the pillow, if you just look at things as they are at one instant, then you cannot really make any statement about causality. But if you look at the history of what preceded what, basically you put a ball somewhere and then its effect propagates with the speed of sound through the medium, and the pillow basically accordingly reacts to that.
It's quite unclear what it means to say that one thing causes another if you lose the sort of context of space, time, and the laws of nature. I mean, one very obvious reason for this is that many accounts of causation, either explicitly or implicitly, make reference to the laws of nature. Many of them also make reference to time. For instance, Hume's own definition of causation was that the cause must precede the effect in time and must be next to it in space, or there must be a chain of adjoining events in space. So we really can't make any sense of what it means for something to be a cause of another thing without time or space, any more than we can make sense of what it means for something to have a colour or to have a shape or a size outside of notions like time and space. The notion of causality doesn't have the kind of purity of a notion, let's say, like number or logical notions, which do make this sort of extra-spatial, extra-temporal sense. And for that reason, to posit a cause of the universe that's outside of space and time, as the Kalam argument must, if it's going to prove anything like the divinity that people like Craig would want it to prove, seems to me stretching the notion of causality far beyond any of its uses that we can actually comprehend.
I mean, some concepts only make sense when applied within the universe or within some part of the universe. I mean, if you ask how much something costs, some table or some chair, then that makes perfect sense and there's a good answer. If you ask how much the universe costs, that doesn't really make sense because you can't step outside the universe to buy it. It could be very similar with cause and effect. Cause and effect is something that operates inside the universe, so it just doesn't make sense to step outside the universe and ask what causes it. Cause and effect is something that happens within the universe, not to it.
We've seen that many cosmologists favor a bouncing cosmology, which may be eternal into the past. Others favor a universe that had a beginning from a spontaneous fluctuation. Another class of models suggests that solutions to Einstein's equations that allow time travel into the past, known as closed time-like curves, could enable the universe to create itself.
This is clearly impossible, for in order to create itself, the universe would have to already exist. It would have to exist before it existed, which is a self-contradiction.
It may be inconsistent for Craig to say that, on the one hand, causes do not have to precede their effects in time, but then on the other hand, dismissing the idea of a self-created universe on the basis that a self-created universe would have to precede itself in time.
So a self-creating universe may appear to be a contradiction if you imagine a linear direction of time, because if you have some cause that leads to our universe, then that cause should precede the effect. But if you have a circular time, then there is really no notion of cause and effect, and because of that, there is no contradiction, because basically all you have is a consistency condition between what happens at one era and what happens at a prior era or future era, because they all just lead to each other. And as long as those consistencies hold, there is no contradiction.
You might have the whole closed time-like curve, and at that level, causality is kind of not an appropriate concept. But if you focus on individual segments of the curve, you might have unidirectional cause and effect just restricted to that particular segment. And so we're right to think in terms of causality at the local level. When we zoom out, causality as such ceases to apply, but we can still do physics. The fact that our intuitive understanding of cause and effect ceases to apply at the global level, that doesn't stop us writing down equations that would describe that system.
In order to assert the universe must have been created by an agent with free will, Craig uses an argument from the medieval philosopher Al-Ghazali, which asserts the universe must have arisen spontaneously, and the only example of spontaneous action is that of a free agent, something we supposedly know from our everyday experience of the world.
I mean, I think it's a pretty good argument. It's just that the premises we no longer tend to accept, the kind of modern conception of the world. The standard view of quantum physics is that it's not deterministic after all, that most interpretations of quantum mechanics have some indeterminism in them. And the most popular approach to understanding free action tends to be compatibilist. It sees free action as compatible with the laws of physics, indeed enabled by the action of the laws of physics. So Al-Ghazali's argument was pretty good, given the assumptions he was making. It's just that I don't think we now have any reason to accept those assumptions.
If you're in the game of appealing to everyday observations, then there's all kinds of things you can say that would be unhelpful to the Kalam argument. For instance, we observe that every event has been preceded by another event, but clearly the Kalam argument can't allow for that. We observe that everything that comes into existence has a material cause, if it has a cause at all, but again, the Kalam argument can't allow for that. We observe that all agency, for instance, all intelligent agency, is material. But again, the Kalam argument can't allow for such things. So everyday experience furnishes all kinds of generalizations that are inconsistent with the conclusion of the Kalam argument. And it's just arbitrary to choose the generalizations that you like from everyday experience and ignore the ones that don't fit with your conclusion.
To summarize, the Kalam cosmological argument is based on an outdated view of mathematics and an outdated view of physics. Mathematicians don't deny infinity, and physicists no longer believe the Big Bang is the beginning. The argument assumes our everyday experience of causality must hold true, even when there is no space or time, but then claims an immaterial mind made the universe from nothing, which is completely contrary to our everyday experience. In short, the Kalam cosmological argument is unsound.